Chapter 3, Lesson 3 deals with scientific notation. The purpose of scientific notation is to write very large or very small numbers in a shortened version. All scientific numbers are going to be written as a multiplication problem with a base of 10. So in the next few examples, we'll show you what that looks like, how you write a number in scientific notation, and what makes a number scientific notation versus what looks similar but isn't scientific notation. So as we go through our notes today, please remember to fill out your notes on your own sheet as you go along. So just as a review, what does 10 to the third power mean? That means 10 times 10 times 10, which we know is 1,000. What does 10 to the negative third power mean? Well, that means write it as a fraction because my exponent is negative. So that means 1 over 10 to the third, and then we know that 10 to the third is 1,000. So we have 1 over 1,000. Now, anytime your base is 10, you can also write this as a fraction pretty easily as well. So if you start with 10 and you want to write that as a thousandths in decimals, you would write decimal point 0. This place would be the tenths, so we put a 0. This place is the hundredths, so a 0. And we have 1/1000th. So this place is the thousandths, so we have a 1. So we can write that as a decimal as well. So 10 to the fifth power is 10 times 10 times 10 times 10 times 10, which results in the answer of 100,000. So you have 1 with 4 zeros, or with 5 zeros. Another way that you can think of it is whenever you have a base of 10, you always start with the number 1. Now, because I have an exponent of 5, if I have a 1 here, my decimal starts here. I'm going to move my decimal 5 spots to the right. So 1, 2, 3, 4, 5. It's now here. So in each one of those loops, I need a 0. So that's another way to see how you can get to 100,000. Now, if your exponent is negative, instead of moving your decimal to the right, you still start with the number 1, but now we move it 5 spots to the left. So that's 1, 2, 3, 4, 5, and then decimal. So we fill in each loop with a 0, so you can see how that would look as a decimal. So that's in the tenths, hundredths, thousandths, 10,000ths, 100,000ths place. And as a fraction, that would look like 1 over 100,000. Now, the reason I'm showing you moving that decimal to the right or to the left based on your exponent is for scientific notation. That only works, again, if your base is 10. So the purpose of scientific notation, again, is to write a large number as a condensed version. So we have two ways of doing this. We look at scientific notation first and write it as a big number, or we have a big number and we shorten it down into scientific notation. What you have to know here, though, is the first number in scientific notation is only going to have one digit to the left of your decimal. All right, so this has the digit 9. The digit has to be something 1 through 9. It cannot be 0. It can be 1, 2, 3, 4, 5, 6, 7, 8, or 9. Your second factor always has a base of 10 raised to some exponent. So if I had something that looked like this, 12.1 times 10 to the third, that would not be scientific notation. And the reason for that is because I have more than a single digit to the left of my decimal. You have to have a single digit. If I have something like this, 4.2 times 8 to the fifth, this is also not scientific notation, and the reason for that is my base in my second factor is not 10. That number right there has to be a 10. So here's my number. I have 9.77 times 10 to the sixth power. So we look at our exponent. Our exponent is 6. It's positive, so that tells me that this number is very large. If it were negative, it would tell me that my number is really small. So the 6 tells me, basically, I'm taking 9.7 and I'm multiplying it by 1 million. Well, an easy way to do that is to identify what your exponent is, and because it's positive, we're going to move our decimal 6 spots to the right. So I start with 9.77, I move it 1, 2, 3, 4, 5, 6, decimal's now there. Each one of those loops gets filled in with a 0. So my very large number is simply just what I have here as, comma, 9,770,000. All right, exponent's positive 4 tells me to move my decimal 4 spots to the right. So it was 2.14. I move it 4 spots, so that'd be 1, 2, 3, 4. Fill those in with zeros. My answer is 21,400. Exponent is 6. I move it 6 spots to the right, move it 1 spot, and then 5 more. So that'd be a total of 6 spots. 1, 2, 3, 4, 5 zeros. So I get an answer of 13,700,000. This next example, notice that our exponent is negative. So that tells me that this is a small number. The negative exponent simply just means move it to the left. So we have 1.3004. I'm going to move my decimal 1, 2, 3 spots to the left. So now I have the number decimal point 0013004. All right, last example has an exponent of positive 6. Tells me to move my decimal 6 spots to the right. So that's 1, 2, 3, 4, 5, 6. So my answer is 2,312,765. All right, all negative exponents here. So my decimal, because my exponent is negative, needs to be moved to the left. On this example, we move it 2 spots to the left. So move it 1, 2, fill in with zeros. Go ahead and pause this. I want you to try the next 3 on your own and then hit play and see how you did. All right, so first one that you tried right here, you move it 7 spots to the left. There was 1 place to move it, so then you had to add in 6 more zeros. Next one should be decimal point 0001256. And then the last one, exponent is negative 1, so you move it 1 spot to the left, decimal point 0376. Now we're going to look at, here's my number in standard form. Now let's write it in scientific notation. So remember, scientific notation only allows you to have 1 digit to the left of the decimal. So you're going to take your 1 digit, which is 9. Everything else is going to be after the decimal. So I'm going to put my decimal right after the 9, and then I'm going to have 876. If everything else is zeros, I do not need to write those, but I do need to account for those in scientific notation. So it's always times 10 to some power. So now the question is originally your decimal was there. We moved it way over here. So how many places did we move it to get to it so it could be in between the 9 and the 8? You moved it 9 spots. This is a very, very large number, so our exponent is a positive 9. Next one, 2,465. 1 digit to the left of the decimal means the 2, and then everything else is after the decimal. So you have 4, 6, 5. Your decimal started there, and we moved it to here. How many spots did you move it? You moved it 3 spots, so it's times 10 to the 3rd power. Now these numbers are all very, very small, so that means my exponents will be negative. Same rules apply. I have to have 1 digit to the left of my decimal, and that 1 digit cannot be a 0. So I start at my decimal, I move to the right, and the first number that is not a 0 will be the number that's to the left of my decimal. Everything else gets written behind it as you see it. So we have an 8, we have a 7, we have to include those in. It's still going to be times 10 to some power. So the question is your decimal started here, but you moved it to here. So how many spots did you move it? That would have been 1, 2, 3, 4, 5, 6 spots. But it's a small number, so it's -6. Next one, first non-zero digit is 2. So we have 2.3. I don't need to include that 0. And then I have to ask myself, how many times did we move the decimal from here to get to here? We moved it 2 times. It's a small number, so it's -2. Go ahead again, pause this, and try the next 2 on your own. All right, so first one should have been 9.26 times 10 to the -4th. And actually, that's not correct. If we move it 1, 2, 3, not 4 spots, so this shouldn't be a -4, it should be a -3. And then our last example, we moved it 1, 2, 3 spots again, so again a -3. All right, so how would you use this in real life? Well, in this example, the monarch butterfly has an average mass of 0.5 gram. If there were 10 million monarch butterflies, write the total mass in scientific notation. So first of all, we have 10 million. What does 10 million look like? 10 million is 10 and then million. So it looks like this. Well, what does that look like as an exponent? That would be equal to 10 to the 3/6/7th power. So you're going to take one of those monarch butterflies and multiply it by 10 to the 7th power. So times 10 to the 7th. Well, this isn't scientific notation because we have one digit to the left of the decimal, but that digit is a 0. So if you were to multiply this out, 1/2 times 10 to the 7th is actually going to be equal to 10 to 5 million. So we have this as our grams, but we need to write it in scientific notation. So one digit to the left of the decimal, and then everything else is 0, so all we have to do is write 5. 5 times 10, and then how many zeros are there? There's 6, so times 10 to the 6th power. Now where this can get really tricky is if you're comparing two different inequalities. So if we're comparing two different inequalities, the first thing we need to do is ask ourselves, what does this number look like? So let's see what that number looks like. So when we write both of those numbers in standard notation, standard form as a large number, even though 2.7 is bigger than 1.97, you have to pay attention to what it's being multiplied by. It's being multiplied by 10 to the 5th power. So you have 270,000, or you have 1,984,700. So which one is bigger? Well, this one is bigger. This number is bigger. So when we read this, we would say 2.7 times 10 to the 5th is less than 1.9847 times 10 to the 6th. So the next example is you're given a option for a job. And in that job, you're given 2 offers, but they're in scientific notation. So pause this, figure out what both of those numbers really are equal to, and then determine which one's the better deal. Many people take one look at this and say, oh, 6.7 blah, blah, blah is way bigger than 4.9. So they think A is the better option. But when you write this in scientific notation, what this is really saying is, okay, you can have $676,899,900, or you can make almost, or $4,990,000,000. Which one's more money? Well, now that you've written them both in scientific notation, you can clearly see that this is a lot more money. So I would hope that that's what you would choose. So scientific notation, purpose is to write large numbers in a condensed version or small in a condensed version, but you have to know what they mean and what they represent. Let me know if you have questions. Otherwise, go ahead and go on to the homework assignment for this lesson. Let me know if you have questions.